Okay, so let's first talk about equations of lines and planes. Nothing lah. Okay, thank you. Okay, so how many? Let's talk about lines first. How many forms are there for equation of a line? Okay, so what's the first form? Okay, parametric. What are the other two forms? Okay, so let's focus on lines first. So lines, there's parametric. What else? Scalar product. Is scalar product form for equation of line? So scalar product is for planes. Okay, so we have vector form, vector equation. Okay, so that's the one that says R equals to A plus lambda n. Right, so do you understand what do each of these expressions mean? So if this is your line, okay, so let's say this is the line. Where is R, where is A, where is M? Okay, let me draw an origin to help you. Let's draw origin here. This summary, summary is not reteaching, so you must be able to answer questions. Okay. A is a point on the line. Okay, very good. Okay, but strictly speaking, we should say that the A, depending on you're saying small a or capital A, okay. So if it's small a, right, it's the position vector of a fixed point on the line. A vector is from A. Yes, correct. All right. Okay. What about M? Direction. What is meant by direction vector? Which direction? What? Which direction the vector is going? You mean which direction the line is going, right? Yeah. Okay. So M is just a vector that is parallel to the line. It can be in this direction, it can be in the opposite direction. But we just need one that is parallel to the line. Okay, so this is M. Then what is R? Any point that is on the line, right? Okay, so for example, what is A plus 0M? Is A, right? So A is one such point. What is A plus 1 times M? Here, right? A plus M, vector algebra. Okay, so this is one possible R. Then if I were to draw the line a bit longer, okay, A plus 2M, this is another point. Okay, so you must understand that this means the position vector of a variable point on the line. It's just like in the past when you learned, say, y equals mx plus c. Right, you have gradient, you have a fixed point, the x-intercept, the y-intercept, and then this is your variable, right? Okay, so now it's just that we are writing it in a different way. So x, y, z. We put the variables into one vector, and we call this R. Okay, then we have a fixed point, which kind of serves the similar role as your y-intercept. Okay, and then your direction vector, which serves a similar role to your gradient. Okay, but in 3D setting, you cannot talk about gradient, right? Because gradient can be in many different ways. Okay, so we need a vector to tell us the direction. Okay, the other way to see is this, right? If I have a line like this. Okay, so let's say this is the line AB. Maybe this is line AB and this is B. Okay, so go back to vectors 1, right? R is on line AB. Another way of saying this is that A, B, and R are collinear. Okay, so maybe you're not familiar with why the equation works. Okay, that's fine. You go back to collinearity concept, right? What does this mean? AR, vector AR is parallel to AB, and therefore is a scalar multiple of AB. Okay, but my AB is M. My AR is OR minus OA, which is R minus A. Okay, so by manipulating the equation, you have R equals to A plus lambda M. That's how the equation comes out. Okay, so there are many ways to see this. Can you go back to the collinearity concept, is clearer. Okay, come. Now let's talk about the other two forms. Okay, so like what some of you have mentioned, we have the parametric form. So how do we get the parametric form? Right, so actually it's derived from this now. Okay, you rewrite the vector equation into its column vector notation. Okay, you will be able to split it into 3 equations. Okay, actually I don't need to write lambda in R so many times, just one time. Okay, so if you think about it, okay, maybe let me explain what is a parameter. So here, at this point, I could say this is the point corresponding to lambda equals 0. I could say this is the point corresponding to lambda equals to 1. This is the point corresponding to lambda equals to 2. Okay, so at each value of lambda, I have 1 point. So lambda works like a tracer, right? As you shift, so imagine you have a slider. As you slide the value of lambda, okay, the point will move along the lines. Okay, so such a variable is what we term as a parameter. Okay, it is like this one single variable that will capture all the information you need for every point on the line. Okay. Okay, so then you may wonder, wow, all this is very complicated. Can we go back to the days where we did y equals ms plus c? Right? So basically you're asking, can we have a Cartesian equation? This is what is a Cartesian equation? Cartesian equation means an equation comprising solely in terms of x, y, and z. There's no what parameter, whatever, right? Okay, so yes, but unfortunately, it's not something that you would like. Okay, it looks a bit complicated still. Okay, so the Cartesian equation, right, is x minus a1 over m1 equals y minus a2 over m2 equals z minus a3 over m3. Okay, where the a's are from this vector, the fixed point position vector, the m's are from the direction vector. Okay, so how do you convert from vector form to Cartesian form? Okay, so the procedure to convert from vector form to Cartesian form is you have to form the parametric form first. Okay, and then for each of them, you make lambda the subject in the equation. Right, so in this case, for example, x minus a1 equals lambda m1. So lambda equals to x minus a1 over m1. You do the same for each of the other two, and then you eliminate lambda. So you equate each of them to each other, and this is what you get lah. Okay. The exception to the rule is what happens when one of them is 0. Right. So what happens if, let's say, the m2 is 0. So maybe we have something like this. Okay, then what you do is you just concentrate your attention on those that you have lambda first. Okay, do what I mentioned, make lambda the subject in those two. Okay, then you just take care of these two will do. For the other one, you have no choice. You have to write it as a separate equation on its own. Okay, because the issue now is that the y is independent of the parameter value. It's not going to change as the lambda change. Okay, so it's not affected by the values of x and y. So this is a line where the y coordinate of every point on the line is 5. Okay, can? Okay, then in reverse, what about the reverse problem? How do we convert from Cartesian into vector form? Sorry? Yes, you go to parametric first. So you precisely do everything in reverse, right? But now you have to remember to bring in the lambda. So you put in the lambda back. You put in the lambda back, and then now you make x a subject. Okay, I should put the 2 in front. Okay, and then you line up such that the lambdas are in the same column. Okay, and then the constants are in the same column. Therefore, y, there's no lambda. So just write 5 plus 0 lambda. Z equals to 1 plus negative 1 lambda. So now this becomes your A. And this part here becomes your M. Okay, follow so far? And this is nothing new lah, it's just a recap. Huh? Okay, now we talk about planes. So again, we have 3 forms. What are the 3 forms? Say again. Vector form. Vector got how many forms? 1 is scalar product, yes. Is there another one? Vector product. There's no vector product. M2. Okay, yes. So from the lines, actually, you see that the parametric form and the vector form are kind of like equivalent. Right? It's just different ways of writing exactly the same thing, right? So in the plane, we're not going to make a distinction between the two. We're just going to say vector bracket parametric form, because we understand that parametric form just simply means breaking down the vectors into their respective components. That's all. Okay. So for planes, right? Because certainly we cannot have one direction vector to tell us all the points on the plane. Plane is 2-dimensional. If you keep going on in one direction, you only follow through one line. Right, so for a plane, we need to bring in another direction vector so that we can generate all other points through the use of the parallelogram law of vector addition. So for example, 2 times of m1 plus 3 times of m2 will give me 1 point. Right, and then maybe negative 1 time of m1 plus 5 times of m2 will give me another point. So you just take all possible combinations of lambda and mu, you will get all the points on the plane. But of course, with 2 is a bit more troublesome, right? Unlike lines, the information can be captured with just one direction vector. Okay, so that's why mathematicians decided, why not, let's try to get another one that perhaps is more convenient to use. So they came up with this form, the scalar product form. Okay, so for a plane, you need two directions. You need two different vectors that are parallel to the plane to encapsulate all the information of the plane. But if you look at it in another perspective, for every plane, there will only be one direction that is perpendicular to it. There is no other. The only other is this way. But just like for direction vector or line, this is something you would expect, right? There are two directions that are parallel to the line. So likewise, there will be two directions that are perpendicular to the plane. Okay, but the point is now I just need to capture all the information in one vector. Okay, so but the question is, how then do we get this normal vector? So do you remember the procedure? Cross product. Okay, so we know that taking the cross product of any pair of vectors, let's go back to vectors one. Taking the cross product of any pair of vectors, what does this produce? Vector. Okay, good, a vector. But how is this vector produced related to the pair of vectors that you took the cross product for? Yes, perpendicular vectors, right? So if you had your M1, M2, there is enough information for you to produce the N. So now I'm implicitly also talking about conversion, how to convert from this form to this form. Okay, so you just take M1 cross M2. Okay, and then the D, how do you get the D? Very simple. D you just take equals to A dot N. Where the A is this one, okay, the position vector of a fixed point on the plane. Okay, so this is how you get from scalar parametric to scalar product form. Okay, then the last one, the Cartesian. Okay, so Cartesian, actually once you have the scalar product form, you can get the Cartesian form almost instantaneously, right? Because R is x, y, z. Okay, your normal vector looks something like this. Okay, once you expand, you have ax plus by plus cz equals. Okay, and this is the Cartesian equation. This qualifies as a Cartesian equation because remember, Cartesian equation means what? Comprising only x, y, z, no other variable involved. So that's like y equals ms plus c lah. It's called the Cartesian equation of a line. All right. Do you know how to go from this form to this form? How do you go from scalar product form to vector form? So let's say, okay, let's take an example. Okay, how to get A by observation?
So like you see, the scale product is something like there is something times 5, something times 2, right? So actually, maybe just take 1, 0, 1, 1, 0, 1, 1 times 1, 0 times 2, 1 times 4. Actually,
Do you follow? Okay. Give me another point. If you follow. Hey, you already get one example. Let the class give another one. Give another example. 0, 2, 0, right? Okay, you can take 0, 2, 0, you can take 4, 0, 0. Because all these are vectors that when you put into the equation, you will get equality. You will get equals to 4. You see? Right? Because you take the dot product. In the first case, it's 2 times 2. This case, 4 times 1. This case, 1 times 1 plus 3 times 1. Sorry, 1, 0, 1. Okay, so all these can be the A. So the A is not really a very challenging problem, but the direction vectors may be a bit challenging now. Okay, but actually there's a trick to it. All you need to do, right, is you can let, so maybe we let X be S, and maybe let X be lambda lah. Let X be lambda, and Y be mu. Okay, so let's see why this works. Okay, now if X equals lambda and Y equals to mu, then we will have lambda mu Z dot 1, 2, 3 equals to 4. Right? Because your R vector is just your X, Y, Z. Okay? So from here, I can expand out the scalar product, and then I make Z the subject. Okay, so now let me put all the information I have together. Then you see some magic happening. All right. So actually what's going on now is I can write 0 plus lambda times 1 plus mu times 0, 0 plus lambda times 0 plus mu times 1. So the parametric form come out already. If you're following through the SLS lesson, you will see that this is a technique that is used a lot in a few of the problems. Like if I want to find the line of intersection between two planes. Okay, those of you who have managed to reach there, this is one of the possible approaches. Right, you let X equals to T. In some cases, you may have to let two variables be maybe S and T, and then you proceed accordingly. Okay, but I would say this is not a very common problem, because like I said, the scalar product form is a more convenient form. Okay, so more logically, you will see problems asking you to convert from parametric to scalar product rather than the other way around. I believe this will be discussed in the lesson. Okay. Okay. Now, okay. So we talk about equations. I want to talk about four perpendiculars and shortest distances, which our friend here has briefly talked about already for one problem. Okay. Ken, any questions about equations before I move on? Do you need me to zoom in, zoom out, anything? Yeah. Okay, let's continue. Okay, so there are two kinds of full perpendicular. One is the point on the line, one is the point on the plane. Right, both problems have been discussed already in the lesson. Right, so let's just refresh our memory. Okay, so there are two methods. For each of the problem, there are two methods. Okay, and for both of the problems, one of the method is to use projection. I feel like it's a one note thing doesn't like this class. Always hanging. Don't know why. Very long time. So I will only space to write for projection method. Okay. So let's. Okay, the first step is always to draw a diagram. Okay, so let's draw a diagram. Maybe at the same time, never mind. I thought about it somewhere. Okay, for a plane, rightfully speaking, you should draw like parallelogram or a oval, right? But actually, for the full perpendicular problem, right, we just need to look at the side view. So if you want, you can also use the line. Okay, sometimes drawing more things doesn't mean that it's wrong. It can be more complicated than so the difference between this problem and that problem. Here, what we have is a normal vector. Right, so this problem we have a vector perpendicular to the object. That one is a vector parallel to the object. Okay, so projection. Do you remember projection how it works? Okay, so maybe one easy way to see projection. I don't know if I explained before. You treat this one as like a wall, right? And then you are shining a light down on this vector here. Okay, the shadow it casts, right, is the projection vector. Okay, and your formula, of course, this is A dot E hat. E hat. You will see this diagram, right? Your summary template as well. Okay, and then this one here. Okay, this one I'm not concerned. Okay, so let's just focus. Okay, so this is the projection vector of A and B, brackets full modulus. Okay, so I'm going to use this idea. Okay, so I'm trying to find this point, the four perpendicular. Okay, so I can draw a similar diagram. Okay, I project vector AP onto M. Okay, so the first step clearly is to first find vector AP. Right, so in a typical full perpendicular problem, this will be given to you. Okay, the position vector of P will also be given to you, or equivalently maybe the coordinates. All right, so to find AP, just take OP minus OA, right? There's nothing much. Okay, then the next thing, what do you do? Okay, so you find AN. Okay, so AN is AP dot N hat. N hat. I'm following the formula there. Okay. Some people so fast CP already. Okay. So next. Okay, then after that, right, you use, so let's say your origin is here, right? This is what I want to find. Okay, so I have OA, I have AN, I can use triangle law of vector addition. Okay, so ON is OA plus AN. Then that's it. Three key steps for projection method. But this one will be more steps because there's a lot of calculations involved, right? You take AP dot M hat, then you divide the magnitude to get the M hat, then that one times the M hat again, right? Okay, now second problem. Okay, second problem is a bit trickier. So we have R dot N equals to B. Here I have A plus lambda N, right? So my OA is A. I already know what is the position vector of the A. This one, if I want to do a projection, do I already have a point? Yes or no? Based on the equation, do I already have a point on the page? No. At least not directly. Right? But I can get one. Remember just now our earlier discussion? Right? How do you get a random point on the page? You just take one that fits. So like 1, 2, 3 equals 4. Then you just take 4, 0, 0 or 0, 2, 0. Okay, something that works. But my advice is to choose something with as many zeros. Because then your working will be easier later, right? So maybe I can take this case 0, 2, 0. Okay, so maybe here A is 0, 2, 0. Okay, so now before you can even find AP, you need to have another step first. You need to find the A. Okay, then next thing, once you have your A, find vector TA. Wait a minute, why suddenly AP become? Okay, there's a reason later. Later you see. Okay, so TA will be in reverse take OA minus. So that means I'm now looking for this one. So the arrowhead is going there. Yes. Okay, so actually, no, let me draw the end here. Okay. Now you draw this way, right? You see that when I project vector TA and what am I going to get? I'm going to get this vector. Right? Because this is the wall now. This is the wall. If this is the wall, you are shining your light this way. So the shadow, the arrowhead going which way? Up or down? Imagine your arrow is like that. Then you shine the light down. The arrow is going that way, right? So the arrowhead go down. And this is the reason I choose to use TA instead. Okay, because when I project TA on N, I will get TN. T capital N. Okay. If you project AP, you can also do it that way. Then you will get vector NP. But your final step will be a bit more troublesome. The final step, right? Once you have your PN is ON equals to OP plus PN. So if you had taken AP here, all these things would flip. So you can still find ON. You will have to take OP minus. Okay, so you see that for the plane column here, take A. Right, by triangle law, I'm going through OA plus AN. But for the plane, actually I'm not going through OA. I'm going through OP, right? Actually, I already got PN, so I can just take OP plus PN to get my ON. You want to go through A also can, but I don't know why you want to do that. Because if you want to go through A, then you have to take OA plus AB plus PN. So why not you just straight away get OP plus PN? Because anyway P is also given, right? Okay. So depending on your destination, you interchange at the correct station, right? You always must direct interchange before you can interchange somewhere else. Oh, yeah. Yeah, I know you say everything wrong. Okay, can. Okay, so this is the projection problem. The projection method for both. I may have space for both methods. Okay, now let's talk about the other method. So this is method one. Okay, method two don't have name, so I'm just going to call it the other method. Okay, so you may prefer. Oh, okay, very good. Okay, now for the other method, right? What we're going to do is we are going to use the fact that n lies on the line. Okay, so how do we do that? Number one, first, okay, since n lies on L, okay, I can say that ON is equal to this. Okay, but you see the difference between this and the equation of line. The equation of line, I'm describing all the possible points on this line. So when I write the range of values, I write in this way, comma lambda in R. Okay, but now I am zooming in my attention on just one point only. So now I say that ON is this for one value of lambda. So like the for somebody or for someone, okay? Right? Yeah. Okay, then
for somebody
for somebody in this country. So R is like a country lah. Okay, so next. Okay, so what I want to do, actually what is my eventual goal, right? I want to use the result for perpendicular vectors. Remember, if A is perpendicular to B, right, it means that A dot B is 0. So I'm trying to make use of this. Okay, so I look at my diagram. I know that my vector NP or Pn is perpendicular to the direction vector. Right? My vector Pn is perpendicular to the direction vector M of the line. Okay, so this will motivate me to first find the vector Pn, which is nothing difficult lah. It's just vector algebra. On minus OP. Okay, but this simple step is very powerful because now I can make use of the fact that Pn is perpendicular to M. Okay, now since Pn is perpendicular to M, the dot product of these two vectors will be 0. Okay, now I already have an expression for Pn, so let me make use of it. So A plus lambda M minus P whole thing dot M equals to 0. Thereafter, in a typical numerical problem, you'll be able to simplify this and solve for lambda. So you will get the precise numerical value of lambda. Okay, which after that, what you're going to do with it is to substitute back into the expression you had obtained in the first step. Yes. Okay, this is the line problem. Okay, so now with this value of lambda, you are going to substitute back and tell us or tell the marker, okay, what is this position vector of n? And then you're going to write your answer. Okay, so I would say that the amount of working for both is about the same. This one may look like 3 steps, but this second step here is quite long. Okay, so it's about roughly the same number of steps. Okay, now for the plane problem, let me erase this diagram. Okay, okay, the advantage of the second method for the plane problem is I don't need to go through the process of observing the A. Okay, so my setup is still the same, it's the same problem, right? What I'm going to do now is I'm actually going to form the line, okay, that is passing through both P and these two perpendicular. Okay, yeah. So now, this line, right? Can you tell me a vector that is parallel to this line? This line. N is a vector parallel to this line. Okay, so if I call this the line Pn, okay, I can say that the equation of the line is R equals to P plus lambda n. Okay, so the idea for the second method is I'm actually looking for the point of intersection between this line and this plane. Okay, because the point of intersection between this line and this plane is precisely the foot perpendicular itself, right? Okay, so do you recall in your SLS lesson, there's one part on how do you find the point of intersection between a line and plane? Remember, there's this problem. You don't remember the procedure, it's okay, but you remember there's this problem. Yes. Okay, okay, so we'll recap how to do this kind of problem, right? So the step one, right, I'm going to attack n through two ways. Okay, number one is since n lies on the line Pn. You see the setup is about, it's a bit similar this, okay? So my On is equal to P plus lambda n for some lambda.
For somebody.
Yes, for somebody in the country, okay?
For some lambda.
Yes, okay? Now, next, not only do I know that n lies on the line Pn, I also know that n lies on the plane. Okay, so just like how n lies on the line means that its position vector satisfies the equation of line, similarly n lies on the plane means its position vector must also satisfy the equation of the plane. So that's what I'm going to say that On of n equals P, because it is part of this plane, it will fulfill the equation of the plane. Okay, so now again it's the same. I have two things, I can use both things together, put this inside. Okay, again solve for lambda. And lastly, work out. So you start this back here and you work out. So this is the four perpendicular problem. So there are four things. Okay, then we come to the last part of this sum. I'm not going to talk about everything in the topic. We are not focusing on equations and this type of problem for today. Okay. So the last thing is the shortest distance. I haven't talked about it, right? Okay. So shortest distance. Let's draw the diagram. So can anyone tell me, right? In the general projection problem, this length, what is the formula? A dot B hat. That's it. Modulus. Sorry. The length. So the length is the length of projection. Okay, then how about this length? A cross B hat. So I mean this one there are few ways, right? There are few ways. Okay, so the most direct way is this. But if you don't like cross product, then you'll be doing the magnitude squared minus magnitude squared. That is Pythagoras. Okay, but I'm going to focus on this. So for shortest distances, I'm going to make use of these formulas. Okay, now so we look at the line problem. It looks exactly like that, right? Okay, so in this case, the shortest distance, right, it will be here, this one. Okay, so I draw again because this one too many things. M, A, okay, and this is what I want to find. Oh, no, this is not A, sorry, this is AP. So using that formula, shortest distance is AP cross M hat. Okay, so the main thing you need to note for shortest distance is that if the question straight away asks you to find shortest distance from a point to line, for example, is there a need for you to find the four perpendicular first? You need to go through all three steps. Oh, then after that, AN, the length. Okay, so the answer is no, you don't have to, because there is already a formula that immediately gives you the value. Unless the question wants both things, then okay, then this is still worth your time, right? But in the exam, if you only need to find the shortest distance, then please don't waste time, okay? Because this is a lot of work, right? So let's go straight to this. Okay, now for the plane, it's a bit confusing. So if you look at this, now it's like that. This is the plane, right? The right angle is here. Okay, this is your end. This is EA. Okay, now it's a bit difficult to see the projection. So let me turn the diagram 90 degrees down. Where is the shortest distance from the point to the plane? This one, right? This is the one, right? Right. This one, is it length of projection of PA N or length of perpendicular? Relative to N, is it projection or is it the perpendicular? It's the projection. So for shorter distance, in the plane context, it is TA dot N. It is not cross. Okay, whether it's AP or TA, it doesn't matter because the modulus will absorb the negative sign. But the important thing here is that for the plane, the dot cannot cross. Okay, why is there this difference? The difference between the problem is because in the line problem, I am using a vector that is parallel to the object. So when I take the perpendicular distance, I'm looking at the perpendicular component. However, in the plane context, the normal vector itself is already perpendicular. It's already perpendicular. It's not parallel. So the correct way to obtain the perpendicular distance is to use the projection length. And this is the further. Yes. Yeah. Anyone else want to watch? Yeah. You want any? Actually, I quickly go.